welcome to our third week of the iCamp Summer School. Our Intercontinental Advanced Materials for Photonics Summer School is a summer school that travels around the world, and this year we hold it in China. We already visited Hangzhou, Shanghai, Qingdao, and now we arrived to Beijing. Yesterday we started this third week of the summer school with the tour to the Great Wall of China. It was a very good beginning of the exciting third week of the summer school. Now it's time to start the lectures, and as you know, the topic of the third week is the photonic crystals and metamaterials. This is just the major topic of the summer school, although we will also continue discussing the other topics of the summer school that we focused on during the first and second weeks of the summer school, in particular electro-optics and biophotonic applications, and so on and so on. And so with this, I would like to welcome our first speaker for this morning session, Professor Lei Zhou from Fudan University, and his lecture, as you can see from the title, will be on metamaterials. Let us welcome our speaker.
Thanks, Ivan. Thanks for a nice introduction. And my flight was delayed for 2 hours yesterday, so I was wondering whether I can get here on time. So eventually I get here in the midnight. So I'm very glad to be here to share with you some of our recent results on the metamaterials. So you can see that the title is a point. Okay. So the lecture that I would like to give is about electromagnetic metamaterials. My name is Lei Zhou, and I come from Fudan University in Shanghai, China. Okay, before my talk, I would like to acknowledge my colleagues, and I would like to acknowledge Professor Lan Lixin's group in Zhejiang University, who is doing the microwave experiment. And I also like to acknowledge Professor C.T. Chen, Wei Jiawen, and Ping Shen from Hong Kong University of Science and Technology, Professor Min Qiu from Sweden, and Professor Tri from University of Delaware, and also my two colleagues, and also these are my students who are contributed to this talk. This is the outline of my talk. So the whole lecture will include the following three main parts. In the first part, since this is the first lecture of this Beijing section, I would like to take this opportunity to give you a very brief historic review of the metamaterials. And then I will selectively give you some of our results on the photonic metamaterials based on fractal geometry, and also I would like to talk about the photonic tunneling, and also I will tell you how can we manipulate light polarizations with the metamaterials, and then I will introduce you our rigorous approach to study the resonant properties of metamaterials, and then I would like to give a perspective of the metamaterials. So now I'm going to give a brief historical review on the fundamentals of metamaterials. I will focus on the three parts. I will tell you that the metamaterial, why the metamaterial is so interesting to us, because it has very special probing wave properties, and also very surface wave properties, very special surface wave properties, and also it possesses very particular wave impedance properties. So the first question we like to ask is, what is the metamaterials? So actually, these two figures represent the definition of metamaterials. For conventional materials, it is composed by the atom. So in principle, nothing is homogeneous except vacuum. However, for the natural material, we can regard it as homogeneous. Why can we do that? Because the structure unit, when the structure unit is much smaller than considered wavelengths, so this material can be homogeneous with an effective epsilon and mu. So such a natural material is homogeneous for light, for visible light, because for visible light, the wavelength is much longer than the structure unit size. That's why we can homogenize these materials. Now, based on the same concept, we can change the structure unit from the natural atom, to the artificial microstructures like this. And then the considered wavelength is much longer than the artificial microstructure size. And this highly homogeneous system can be homogenized as an effective homogeneous system with a well-defined effective epsilon and mu. And this is called metamaterials. So the definitions of a metamaterial, which I call here for short MTM, is that it is kind of artificial composite made by wavelength resonance microstructures. And this a microstructure system is much smaller than the considered wavelengths, so that we can homogenize the whole system. And why we do that? Because if we can tune the properties of this structure unit, we can have arbitrarily even negative values of epsilon and mu. And so that the system can possess well-anomalous EM wave properties. A very typical metamaterial sample is shown here, which is fabricated by the UCSD group in 2001. And this is the picture of this metamaterial sample. So now you may ask, why we fabricate that kind of metamaterials? Because the metamaterial can extend our material phase diagram greatly. If you look at this phase diagram, the 2D phase diagram, which is based on the epsilon and mu axis, you will find that the natural material is very limited. For natural materials, some are located here and some are located here, and very rare are in this fourth region. And if you look at the dispersion relations, you will find that in this region, the system is transparent. And in these two regions, either epsilon or mu is negative, so that the wave cannot penetrate inside, so the system is basically opaque. However, we do not have natural material to locate here. So this is basically an empty region based on the natural material. Now, fortunately, if we now we can use the concept of metamaterial, we can basically fabricate every kind of material to fill all these 2D maps, and in principle for every frequency. So, based on metamaterial, we can have a much expanded material phase diagram. And if you look very carefully at this phase diagram, you will find that in some of the regions, the metamaterial can have very anomalous property wave properties, and also have very anomalous surface wave properties, and also it has very anomalous wave impedance properties. So that is what I summarized here for three different kind of anomalous EM wave properties for metamaterials. Now let me briefly introduce you the first part to tell you what the anomalous property wave properties that the metamaterial can possess. Over 40 years ago, a Russian scientist was able to prove that for a media with both negative epsilon and mu, and he found that if you look at the dispersion relation, you will find that the basically the reflection index is still real, because the n squared is equal to epsilon dot mu, and either if both epsilon and mu are negative, the product of these are still positive, so the system is still transparent. However, if you look at the point vector, you'll find that actually here, the point vector is antiparallel to the phase vector, and it's very easy to prove like this. So that means for these anomalous materials, when wave probably like this, the energy is transported like this. So sometimes this system is like it's called the backward media. And if you look at carefully about the EHK relation, you will find that the E vector, H vector, and the K vector, they satisfy a left-handed rule. That's why this media is often called the left-handed materials. In contrast, for normal materials, this 3 vector will satisfy a right-handed rule. So what happens then? The first consequence is that if you look at the refraction behavior, if you shine a light from a normal media such as air onto an interface between air and this left-handed material, you require that the key parallel should be conversed here, and then you have to also require that the causality, that means the energy inside the media should be like this, should be leave the interface rather than approach the interface. If you impose these 2 conditions, you will find that the refraction is like this. So that's why sometimes this system is also called a negative refraction index materials. So you can, for normal materials, light going like this and then bend like this. However, for this media, light going like this and then they bend like this. So then that means the refraction wave and the incident wave, they are on the same side of this normal direction. So that is called negative refraction. And even interesting, you will find that for flat slab of materials, both epsilon and mu equals to -1, and this slab can behave like a lens to focus a point source from here to here. And this is very easy to prove because for each light, because the refraction index is negative, so it bends like this. So for each ray, it will focus to the same focal, and then the second interface is focused to another point. So this is the very famous proposal of Vassalaro that is flat material can behave like a Vassalaro lens. And also they have very special, very particular inverse Doppler effect and inverse tranquil radiation, so on. Now you may ask the question that if both epsilon and mu are negative, then something will be wrong because if you look at the energy density, you will find that energy density will be negative. So is that wrong? So that's not wrong because this equation is only for non-dispersive media. For dispersive media, the energy density should be relating as this. And therefore, if both epsilon and mu are negative, and if this equation is still be satisfied, so the energy density is still can be positive. So that means that the matter material should be dispersive. It only has negative epsilon and mu at a particular frequency, but at other frequency, it may not be negative at all. So it should be dispersive. And the dispersion of epsilon and mu should satisfy these equations. That is the causality requirement. Now the proposal has been proposed for over 40 years ago. However, it's only attracted attention only recently. Why? Because it's very difficult to really make left-handed materials. Because if you look at the requirement, you will find that negative epsilon actually is very natural because we have free electrons in the metal, and the free electron plasma will give us the negative epsilon naturally. However, the negative mu is much difficult to obtain because we do not have a magnetic monopoles, so we do not have natural magnetic plasmas. So the breakthrough comes from the breakthrough is purely after Professor John Pendry proposed 2 structures which can have negative epsilon and negative mu at low frequencies. For this structure, he proposed that for low frequency we do not have plasma at all, so we can have, however, we can make some kind of electron resonator system to still have an effective epsilon at the low frequencies. And even interestingly, he proposed that we can have split ring resonator structures And if this structure is on resonance, the current is flowing like this. And so the current will have a very strong magnetic resonance, so that the system can behave like a magnetic resonator. If you combine this structure and this structure, and if the wavelength is still much longer than the feature size of these structures, the system can be homogeneous, just like the concept of metamaterial. So then the composite material will have a negative, will have effective epsilon like this and effective mu like this. So if you can tune carefully the resonance frequency of this, the E resonance and also the resonance frequency of this magnetic resonance, very possibly we can have a common region that both epsilon and mu are negative. So that's the region that we have the left-handed material. So after the proposal of John Pendry, the UCSD group fabricated this very famous negative index material sample, and they demonstrate that this sample indeed possesses a negative index. And this is the wedge sample that they fabricate, and they shine a EM wave. Actually, it is a microwave onto the sample. And if the system possesses a positive index, and then the refractive wave, it will go like this. And if the system possesses negative index, the refractive wave will go like this. So that is the experiment. Indeed, for positive, they have the positive refraction, and for this material, they have a negative refraction. After this famous experiment, some of researchers have very hot debates on this. However, the following work, several PILs in 2003, support this negative refraction phenomenon. So I think after 2004, so nothing will question this negative refraction phenomenon. For more details, please see the review in Science. So let me go into the second part of the anomalous wave properties of left-handed of the metamaterial. It possesses very anomalous surface wave properties. So what is a surface wave? The surface wave is actually an eigenwave solution bounded in an interface between air and the metal. This is very famous picture of a figure of this surface plasma pearlitones bounded at the air-metal interface. And also we can have extended surface plasma on the flat surface, and also we can have a localized surface plasma on the small particle. Another feature is that the wave will exponentially decay as leaving from the interface. And this is showing the exponential decay. So why are we interested in the surface plasma or surface wave? Because it has many applications. It possesses two very important features. One is the surface feature, and the other one is filling acid feature. Because of this, it has many applications. For example, it can be used in photolithography. It can be used to detect a single molecule, and also it can be used to survey the imaging, etc. However, for a natural material, for example, metal, if you look at the surface wave at the air-metal interface, you'll find that there's many restrictions on the surface wave properties. First, the transfer electron mode does not exist. Second, it only supports the TM mode dispersion, and also the resonance frequency is fixed by the natural frequency. So this is the typical TM mode dispersion of the surface plasma, and you will find that it has many restrictions. This plasma resonance frequency cannot be changed. It can only be fixed by the material itself. Now with metamaterial, we have a much expanded phase diagram. So this is the paper that I wrote with Professor Chen in 2004. Basically, we plot the phase diagram of epsilon mu, and we found that for this expanded phase regime, the surface wave properties is much more interesting. In particular, in some region, both T and TMO can coexist in this region. In this region, we only have TMO TM polarized surface wave because we have metal here. And in this region, we have TE polarized surface wave. And in this third region, and when some conditions are satisfied, we can have both TE and TM mode. In particular, if you look at this special point, when both epsilon and mu equals to -1, you find this is a common cross point for many fixed boundary. At this point, the surface wave is very particular. It's very special. If you look at carefully with the solution, you will find this particular stage can allow the surface wave with arbitrary K vectors. This is very special point. And it is Pendry who first observed this special point, and he soon realized actually the Vassalagro length proposed many years ago is actually a perfect one. So in this pioneering work, Pendry did a calculation, and he found that these lenses can not only collect all the Pauling wave components from the source, but also be able to collect the avalanche component radiation from this simple source. And for the radiation, conventional lens, we cannot do that because the conventional lens do not have surface wave at this for this to cover this enhancing wave. However, because we have at this particular point, we have surface waves for every K vectors, so that we can collect every enhancing component. That's why Pendry said that this Vassalagro lens is actually a perfect lens. It can form the perfect image. On this famous paper, very hot debate, a Spanish group point out that actually is not correct, because if you do that, you will find the energy will diverge at this exact interface. The reply of Pendry is that the perfect lens is indeed impossible. However, super lens, if you add some laws into this material, the super lens is still possible. Super means that we can still be the common diffraction limit, the λ/2 diffraction limit. However, even the debates on the single frequency properties are solved. However, the pioneering FDD simulations rose the many puzzles for the perfect lensing. In 2000, a group in US, they did FDD simulation to study the perfect lens effect. The results are rather discouraging because they found that there's no steady state focal were found, and the field varied dramatically over time. You will find this statement here. And several years later, a group in Singapore reported that this oscillation is actually very feature oscillations with a very defined frequency. And this is report the image as function of the frequency, as function of time, and they found that this beating phenomenon. So the question arises, what's the origin of this oscillation? CT and I, when I was still in Hong Kong, we did a study to solve this puzzle. In short, we found that this super lens or super image has actually super prices. The first price to pay is that the image oscillation is actually inevitable. It's already there because it's caused by the beating effect between the working frequency signal and the vortex, very special vortex-like surface wave mode, which is there for all the electromagnetic systems. For this vortex-like surface wave, the energy flow like this and then go opposite direction inside the lab. So this mode does not transport energy at all. So when this mode is excited, it cannot be dissipated if there's no loss. However, if you add loss, you can have fast convergence, but you also destroy the image. Another price is that the super. If you want to have a super resolution, you have to wait for super long time. And the waiting time, the stabilization time is exponentially related to the resolution you have. For the super resolution, you have to wait for super long time. So that gives us a very awkward dilemma. So if we can add loss, we can have a fast convergence to reach a stabilized image. However, the price is that the final loss will destroy the image resolution. So how can we solve this dilemma? Now we got a solution. In this paper, now we found that we can have another freedom to suppress this oscillation. Because we know that this oscillation is caused by the beating effect, by another with another surface wave properties. And if we can choose appropriate switch on time to avoid exciting this surface wave, we can suppress this oscillation without destroying the super resolution at all. So this is the calculation result. Indeed, we can have an optimal switch on time in which we have a very good solution and we can suppress the oscillation. So the conclusion is that the super imaging is still possible. However, we have to implement with some care. Now I'd like to switch to the third part. I will introduce to you then the anomalous wave impedance property that the magnet material can possess. This anomalous wave impedance properties is often overlooked by the researchers in this field. However, it's actually very important. If you look at the EM wave theory, you'll find actually the refraction. I'm sorry, should be refraction. The refraction is governing by the refraction index n, which is related to the product of epsilon and mu. This is called Snell's law. However, the reflection is governed by another quantity, which is actually the impedance, which is square root of mu over square root of epsilon. If you look at if you calculate it carefully, you will find the reflection index, the reflection coefficient from air on the magnet material interface will be given by this equation. Now, if the material is a metal, because metal have very low impedance because of the epsilon is very large, and then you put z equals to 0 to this equation, you will find that r equals to -1. So that's why the metal reflects EM wave perfectly. However, it has to possess a phase reversal, the pi phase change. Now, more freedoms are offered by the magnet material because the impedance can give us more freedom value. Because the impedance is given by is fixed by not only epsilon but also mu. Because the magnet material can have arbitrary value of epsilon and mu, it means that the impedance can take arbitrary values upon careful design. That means the reflection phase, if we define the reflection phase like this, the reflection phase can take arbitrary values. In particular, if you define a system with mu tends to infinity, you find that reflection now is actually in phase. The reflection phase is actually 0. And in principle, we can realize any kind of reflection phase. The phi is not only pi, but also from very continuously from 0 to pi. So we can realize any reflection phase with a magnet material. Indeed, we can do that. Actually, this famous structure appears before the concept of magnet materials. And Dr. Simon Piper from Eli Yanovitch's group proposed a famous structure which is called the mushroom structure in this year. And he found that the reflection phase can change continuously from pi to -pi. So therefore, there must be a frequency at which the reflection phase is exactly 0. And in recent years, we found that actually we can characterize this kind of they call this system high impedance surfaces. In recent years, we found that we can characterize this very complex high impedance surface by a magnet material model. And we found that this kind of system can be described by a double layer effective media model, which is a metamaterial magnetic layer put onto a perfect layer. So basically, we can design a metamaterial which can possess an up to value of refreshing phase. There are many applications of such anomalous impedance properties. Let me introduce you some of the examples that we have. The first example is that we can fabricate vertical wavelength cavities. If you look at the condition to form a cavity mold for this cavity, you find that this equation is a very famous condition. That means the accumulated Brownian wave plus the reflection phase at this interface, the sum of this should be a multiple of 2 pi. For conventional materials, the delta phi for 2 interface is just pi, so nothing special happens. However, if we replace one of the materials from by a metamaterial, because the delta phi can take any value, so immediately you will find that the size is not bounded as half wavelength at all. It can have a much smaller thickness of this cavity. And indeed, we did experiment to show that indeed for this special arrangement of cavity, we can have a vertical wavelength effect. And also we extend the idea to the 3 dimension, and also we fabricated a all-dimensional wavelength cavity, which is not bounded by the half wavelength at all. There's some other interesting properties of this special reflection phase. For example, I think many of you are very familiar with the photon bandgap effect, because the photon bandgap is caused by the Bragg scattering. So you can imagine that a 1D system can only support a 1D partial bandgap. For example, this layer system, it must have a 1D partial bandgap, and for this direction, it does not support any bandgap at all. So, however, the picture changes if we use the negative index materials. So in this paper, our Australia group proposed that if you use negative index materials, you can have a 1D system like this to support a 3D complete bandgap like this. So why can this happen? For this direction, the bandgap is caused by the periodicity. Caused by the Bragg scattering, which is very easy to understand. So how the light can be stopped for this direction? This is very interesting, particular. If you look at the wave along this direction, you will find that the Gaussian mode can exist only when this condition is satisfied. Phi p is the Brownian wave phase accumulation, and phi r are reflection phase change. Now the physics arise just in this reflection phase. For conventional material, we cannot have a system to let this condition not satisfy. However, if we can have a negative index material, we can have some special arrangement, some special parameter to let this condition not satisfy for any frequency. So that's why this system can support a bandgap along this direction. So this also caused by the special reflection phase properties. 2 years ago, we extended the idea to anisotropy metamaterials. In the previous Australia group, they proposed the system to be composed by the isotropic negative index material. However, the isotropic material is very difficult to fabricate. And my student, Shu Ying, extended the idea to anisotropic material. We found some of the interesting physics. We found first, only m equals to 1 mode is okay to open this complete bandgap. And also he found a very complicated parameter conditions for this anisotropic material. And also, because we have this extended parameter regime, because we have more freedom to choose parameters, we can have more extended phase diagram to support this complete diagram. So let's conclude this part. I think I just gave you a very brief and very incomplete historical review of the magnet material. And I would like to convince you that magnet material has very unusual EM-wave properties, including anomalous property wave properties, surface wave properties, and wave impedance properties. And in the following, I will introduce many extraordinary wave phenomena discovered based on the magnet material. So shall we have a brief call?
Questions? Are there questions? Yes, please.
I'm quite curious about experiment where we have wave propagation and energy propagation are anti-parallel. How can I imagine it? Something.
Experiment?
Yes.
The indirect experiment is net reflection.
Okay.
Yeah, that's the indirect. And also the a group in the, let me see, in Germany, I think, which is led by Martin. They really did an experiment to measure the phase delay of this of the pulse across the slab. They really found that the phase inside this one is negative. So you can look at the I think this in Nature paper published about 2 years ago.
Are there more questions? I have a question.
Yeah.
It seems that most of the materials so far have been non-fabricated, especially if people want to use them in near-infrared or actual light. Then it's very challenging because the features become very tiny. So are there some attempts to build those materials using self-assembly approaches that you can mention?
Yeah, some of the efforts are already there. I already know that this concept, the whole concept of magnet material is based on the design. So if you use the self-assembly and you inactively introduce the randomness, or I don't know, because you have to have the very small structure of unit, and structure unit have to be well. I think this is a big challenge in the short wavelengths. That's why the optical magnet material is still not so much. Geometry, and also magnetic magnet material, and also plasmonic magnet materials. Actually, before the concept of magnet material appears, in fact, the fractal has been widely used in the photonic community. It's widely used as antennas because the fractal has multiband and also it's very compact. And you can see the review in this paper. And also, its optical properties have attracted many attention because the fractal has similar properties. And if diffraction, it can be used as diffraction gratings. And also you can see these references. And we combine the concept of fractal with magnet material. By the same way, I mean that Professor C.T. Chen, who is sitting there, and Professor Wen Weijia, and also Professor Shen Ping from Hong Kong University of Science and Technology. And we combine the concept of fractal with magnet material, and we found that we can use this concept to fabricate a very good quality fractal electrical magnet materials. And also we can fabricate fractal magnetic magnet material. And recently we found that we can even fabricate fractal plasmonic magnet material with very particular surface wave properties. The motivation that we do is that we notice that the fractal has two very good properties. First, it has a surviving response. That means the fractal can respond to a much longer wavelength. And besides of this, it also has multi-band functionality because the self-similar properties. For a particular frequency, if the fractal can respond, it can also respond to another frequency because it has self-similar properties. And my talk is entirely based on this recent review, which is serving as a chapter in the Springer book, the Metamaterials Theory, Design, and Application, which will be published in this year. Now, first, let me introduce the concept of fractal electrical metamaterials. And this paper is published many years ago. You know that in that years, we do not realize that this system is actually a very good quality metamaterial. And we still look at focus on the photonic bandgap effect at that years. And after the paper and also when the metamaterial concept is taken up, we found that actually this is a very good metamaterial. So the fractal structure that we take is basically depicted here. And it has the H-shaped structure. This is another structure, the H-shape. And scaling factor is 2. That means we scale this H-shaped structure by a factor of 2 and attach to the 4 ends of this structure. And this is another generation. This is the third generation. And basically, we said this is the first level, and this is second level, and this is third level, and so on. So this structure is the 6th level fractal structure. This is a picture of a realistic 15-level metallic fractal that we fabricated in the laboratory. You can see that this is the first line, which is very thin, and this is some structural details. The first line is this, and the line width and the width are both very tiny, and also the entire structure is printed on the PCB substrate, and this gives us the whole 15-level metallic fractal plate. So we perform experiment to measure the transmission and reflection spectra of the fractal plate. Surprisingly, we found that there are several bands inside which the transmittance is strongly attenuated, which resembles very much the concept of photonic bandgap materials. And even surprisingly, we found that in between these two band gaps, there always be a frequency regime where the transmittance is equal to 1. It's almost equal to 1. And also we found that this structure naturally possesses multi-band and self-similar response. You notice that the horizontal axis, the frequency is scaled by the log scale. So the log scale means if you have a pure density, that means the structure is actually self-similar. You can understand this. And we perform the FDD simulations. The simulation result is plotted as a blue line, and you can find the perfect agreement between theory and simulations. To understand this very particular, very intriguing phenomenon, we perform we construct a model to characterize this response. We notice that actually the structure, although it's very complicated, the structure, the wavelength is much longer than the structural details. So that's exactly the situation where the concept of metamaterial can apply. So at the frequency that we are interested in, we can homogenize this system as a homogeneous materials with a well-defined epsilon and mu. Now that we already have transmission spectra, we then retrieve the effective parameter of this effective plate. And we found that actually this fractal plate, although it's very it can be homogenized as a homogeneous plate with effective permittivity like this, which is given by a series of electrical resonance. And you can find that the dispersions of epsilon effective is given by a series of E resonance here. This model gives a very good agreement with the brute force FDD simulation. The brute force FDD simulation is given by the dot, and the model result is given by the line. You can find a perfect agreement between these two. So at that time, we realized that actually this fractal plate is a very good quality electrical material with well-defined permittivity. And also this effective immediate model naturally gives an explanation why the total transmission can happen. In between two resonance where the total reflection happens, we always have a particular frequency where the effective Flaherty constant equals to 1. That means the system becomes transparent at these particular frequencies. That's why at this frequency the total transmission can happen. Physically, this happens because the two currents for these two resonances are just out of phase and they cancel each other, seen at the far field. So what's the physics? We found the physics is governed by a series of self-similar local resonances. This is a typical picture showing the distribution of the current. You can find that for a particular resonance frequency, the EM wave will excite the current along a particular line, and then the current will flow to the ends of the structure. For another frequency, the excitation will excite another line, and then the resonance frequency is indifferent from the lower frequency one. This is the lower frequency, and this is the higher frequency resonance. So the resonance frequency can be changed by changing the structure. If you want to have a lower frequency, you just scale the system to a larger scale. If you want to have a short wavelength, and you just scale the whole system down by factor. So that means we can design the structure to have any permittivity that we want, basically. Another property is that the structure can have a wavelength response. In these 2003 APL papers, we did an experiment, a simulation, to demonstrate this wavelength effect. For a model antenna, which is here, we put an object here and want to block the radiation. And we measure the radiation pattern here. We found that if the object is a small plate of metallic plate, we found that when the wavelength, when the half wavelength is longer than the size of this metallic plate, I mean the perfect metallic plate, the EM wave cannot be blocked. You can see that these two frequencies, which is a lower frequency, and the radiation is actually not blocked. And even interesting, we find that the radiation along this direction is even higher along this direction. So that means a metal plate cannot block the EM wave at all. However, if you replace the metallic plate by a fractal plate, the 6-level fractal plate of the same side, you find at this particular phase, it can reflect EM wave very efficiently. This is radiation pattern given by the fractal plate, and you can find it can reflect the EM wave very efficiently. Note that at this wavelength, the wavelength is much longer than the total size of this fractal plates. The fifth is that although the whole structure is much smaller, it can respond to a very long wavelength. That's why it can reflect the EM wave. So that is very useful for miniaturization technology. So the fractal plate has a wavelength response and also has a multi-band response. Now I'd like to introduce the nanomaterial. So you can see that for the single plate of metallic fractal, the effect medium shows that this system is basically still a electrical response. So the question is, how can we make it magnetic? We found that we can add another metallic sheet on the back of this substrate. So this inside layer is the dielectric substrate, and this is a metallic fractal plate. And on the other side, we have a perfect metallic sheet. And this whole three-layer sandwich structure is actually a magnetic materials. And we perform an FDD simulation to calculate the property weight properties. Because this system is totally reflecting, because it has a perfect PEC layer on the back. So only the phase can be relevant. And this is the phase repeated here. And remember that I have shown you that if you have magnetic response, the reflection phase will be in phase. So indeed, you can see that at most frequencies, the reflection is still like metal. However, at some frequencies, the reflection phase changes continuously from pi to minus pi, indicating that a magnetic response appears here. So we performed the experiment to demonstrate this idea. So how to demonstrate this idea? We attach a very small antenna just on the top side of this fractal plate. Because the radiation of this guy is actually an interference between its own radiation and its refracted wave. If the reflection is out of phase like metal, no radiation can be detected in the far field. If the reflection is in phase, the interference will be constructed. That means that the total radiation will be strongly enhanced. So indeed, you can find that at this particular frequency where the magnetic response is predicted, we do find that the radiation is strongly enhanced at the peak. That directly demonstrates that indeed at this frequency, a magnetic response is here. So this is the direct experimental demonstration that indeed this system is very good magnetic material. And also, in fact, we found that this complex structure can be modeled by another effective linear model. Note that for this structure, we cannot use the single layer of nanomaterial to characterize this structure. We have to use a double layer. We found that this structure, although it's very complicated, can be modeled by a double layer effective medium model, which is a homogeneous magnetic material put on the top of a PEC layer, the metal layer. And the mu tensor is given by this form. And we found that this system behaved very well to describe all the properties of these complex structures. Indeed, we found that our model can work for all kinds of these complex structures. You can replace the fractal structure by this cross structure, and you can also replace it as a square structure. No matter how complex these structures are, for this kind of three-layer system, you always can characterize this kind of complex structure as a double-layer effective medium model, which is composed by anisotropic magnetic material put on the perfect electric conductor. And we can demonstrate this idea by considering both the reflection phase properties and also the surface phase properties. For the reflection phase properties, we found an effective medium model gives a perfect agreement with the FDD simulation on the relaxed structures. You can see the agreement is quite good. And even the agreement, the model can describe very well the surface phase properties of these relaxed structures. This is a dispersion diagram given by effective medium model of the double layer system, in which we found that we predict a surface wave bandgap here, and also we have two band here and here. And we perform an FDD simulation to study the transmission on the relay system structure, and indeed we found a band gap is shown here. So that demonstrate that this doubly effective medium model can perfectly describe the host, the realistic structures. Okay, now let me introduce the third part of this fractal material, metamaterial, and we recently found that actually this fractal idea can give us more structures. It can give us the fractal plasmonics metamaterials. And this work is done by my two students, Xueqin and Shi. Let me go back to this slide. The surface plasmon is very important in modeling technology, and we have two kinds of surface plasmons. And we have medical application of surface plasmons, so that's why the surface plasmon or surface wave attracted much attention recently. However, there's a problem for natural material. For natural material such as silver and gold, its plasmon frequency is fixed by the electron density. For example, for silver, we have the plasmon resonance frequency, which is fixed by this frequency. Now the question arises, can we have an artificial material with arbitrarily selected plasmon frequency? I want to have a plasmon resonance which is not like this in the visible wavelength, but in the, for example, IR frequency, or in the terahertz frequency, or in the microwave frequency. So if I want to do that, how can we do it? There are quite some methods. The first method is to change the effective electron density so that you can change the plasmon frequency. You can use the idea of semiconductors. You can use the metal dielectric composite and also metal dielectric multilayers. By adding some dielectric layer inside the metals, you can decrease the electron density so that the plasmon frequency can be lowered. However, this is not easy to cover the entire frequency spectrum. The tunability is very limited. It can only cover a small range of frequency. And also you can have a broad scattering mechanism to change the surface plasmon band structures. And in this famous paper, then I will go back to this paper again. In this paper, you will find that by using broad scattering, you can fold back the surface plasmon band into the first Brillouin zone. However, this limitation is that broad scattering can only fold back the band, fold the band. It cannot change the plasmon resonance frequency fundamentally. And also, there's some recent idea. For example, in 2004, John Pendry proposed a structure and found that for this kind of structures, if you insert a very high index material inside the waveguide, inside this square-like waveguide, you can mimic the surface plasmon properties. The limitation is that you have to insert some kind of high index materials. The high index material is not so easy to realize, especially in the high frequency. Okay, our motivation is the following. We want to construct a plasmonics metamaterial without using high index insertion. The system can support surface plasmon with both polarizations. And also the system can process any desired surface plasmon frequency. It can not only work, upon design, it can not only work for the high frequency, but also work for microwave frequency, for the terahertz frequency as well. The borrowed idea from the fractal concept, our structure is actually a metallic plate drilled with fractal-shaped slit. This is a perfect metallic plate, and we drill some kind of metallic shaped slits. This is a 4-level fractal, and this is some slit, and inside which the air is filled inside. So we found that, okay, this is the structure details. Yeah, I do not want to go into details of this structure. Why we abort this idea? Because we understand that fractal is itself a wavelength, so that we do not need to high index material to lower its response, to lower the whole structures. So that's why we think that this structure perhaps can support well-defined surface plasmons. Indeed, we performed FDD simulations on the relaxed structures to calculate the surface plasma polariton band structures of this system. And we found that we have two very well-defined surface plasma band for two directions. Because the structure is inherently anisotropic, the surface plasma band for this direction, gamma to x, and for this direction, gamma to x prime is different. However, for each direction, we found two very well-defined flat SPB band. We employ the idea of an ATR technique to identify the polarization state, polarization properties of this SPB band. And we found that for this frequency, while for this direction, the SPB is T-like, polarized. For this direction, this is TM-like, and this is T-like. So that means this structure can support surface plasma polariton with both T and TM polarization without high index insertion. Yeah, I just forgot to mention that for natural plasma material, for example, for metal, it can only support TM polarized surface plasma. That's why if you want to use it as an image device, you have to make sure that the radiation from the source only contains P polarized wave, TM polarized wave. However, if you look at the band structure here, you will find that our structure has an advantage, and it can support both T and TM polarized surface plasmas. Now let me compare the structure with other structures. This is another structure which is proposed 2 years ago by another group. And they propose that actually we do not use the square hole, but rather use the rectangular holes. And he found that this system can support TM polarized surface plasmons without using high index materials, which is good. However, this limitation is that this structure only supports TM polarized surface plasmon along this direction. It cannot support any surface plasmon along these directions. Okay, if you compare our structure with this rectangular hole structure, we found that indeed this structure only supports TM polarized surface plasmon. So by comparing this one with this one, you can clearly see that the advantage of our structure is very clear. Now the question is how to tune their plasma frequency, plasma resonance, plasma wavelengths. How to tune this? This is very easy. You can change without scaling the whole size of the periodicity. You can simply change the line width and also add some levels. You can already very efficiently change the resonant wavelengths. This is shown here, and we just change the line width of the fractal structure, and can already have a very wide tunability. And also, if you tune the whole size of the fractal structure, scale down from you can have resonance from microwave to far infrared very easily. So the conclusion is that we have obtained a plasmonics material based on fractal geometry to support the surface plasmons in both T and TM polarization without high index material insertions. Now the question is, do we have any applications? I already mentioned that in 2000, Pendry proposed that the negative index material can behave like surface perfect length. And even you do not have a negative index, if you have a negative epsilon, you already have also a super length. So this idea is demonstrated by the Professor Zhang Xiang's group in 2005 in science paper. and they used the silver slab as a superlens, as a near-field superlens, and they found that it can enhance the resolution very dramatically. Now, there are two shortcomings of this structure. The first is the natural material, silver, the plasma frequency is fixed. It can only work for single frequency, which is in the visible light. Another limitation is that the silver supports only TM polarized surface plasma. So that's why the Johnson's group, they have to carefully design their radiation source to emit P polarized waves only. Now the idea is, can we apply our plasmonic material as a lens? Indeed, we found that we can. We performed FDD simulation to study the imaging in the infrared frequency region. This is two sources placed at this. If we without lens, and we measure the field distribution along this direction, on this plane, we found that the two sources cannot be distinguished. If you use the rectangular slit lens, which I mentioned before, you'll find that it can be distinguished along this direction only. For this direction, it do not exhibit the wavelength features at all. If you replace the rectangular slit lens by our fractal plasmonic material lens, you find that the two sources are very clearly distinguished with very good resolution. Now let me study another orientation. Now before the orientation is like this, now the orientation is like this. Still without lens, for this orientation, the two images cannot be separated. For the rectangular slit lens, because it does not support surface plasma along this direction, so that for this case, it cannot separate the two images, or it just blur. For our fractal material lens, you can still see that these two images are clearly distinguished. So the conclusion is our system does work as a super lens for all-dimensional subwavelength image. Now we change to microwave frequency region to perform the imaging experiment. The experiment is done by Professor Zhang's group in Zhejiang University. The structure is slightly different from ideal fractal structure. The structure details is shown here. And we found that for this resonance frequency, which is the plasma frequency of this structure, and we put antenna working here, and then we put another antenna on the back of this lens, which is very safe, and to measure the field distribution. This is basically what the experiment has been done. Indeed, you find that if we put an antenna here and put another antenna along this direction on the other side of this lens to measure the field distribution, you'll find that if without the lens, the field distribution is very broad. It's very broad without any resolution. However, if you add our fractal lens here, you find that the field distribution is very signified, and also it has a very good resolution. If you look at the wavelengths, you'll find that the image resolution is about lambda over 15, which is very wavelength. And also the field is strongly enhanced in the if we add the fractal lens here. We then perform the FDD simulation. We found a perfect agreement between the FDD simulation and the microwave experiment. Compared with the silver lens, a shortcoming of our structure is that our structure is not homogeneous along in the lateral direction, so that the image resolution must depend on where you put your source. So we measured 3 different situations, which is defined by the duration of the source from the center. For the situation which is very near to the center, you find that it is clearly distinguished. For the deviation, for the relatively large deviation, you find that it's still distinguishable. And only in this situation, then the length is just set at the boundary between two unit cells. We found that this length cannot be distinguished. It's split into two equally highly images. So by considering all this, we found that overall resolution is actually bounded by the periodicity of the whole structure. So for this structure, it's still much wavelength, and we calculate this one, and we find that the overall resolution is roughly lambda over 7, which is still wavelength. We compared with our lensing mechanism. We found that we do have some unique properties. In 2005, Kawada's group in Japan proposed that you can use this localized surface plasma of a metallic rod to make a metallic lens to focus some images. Another group in England, they proposed to use a waveguide mode transport to use the wire media to perform the imaging. Compared with this, we found that both of these structures, they depend on the lens thickness, and our lens is independent on the lens thickness. So it's possible to be a good candidate for far-field imaging if you can make the device thicker and you can transport the image to a long distance. Now comes to conclusion of this part. We combine the fractal and the magnitude concept. We can design photonic nanomaterials with very rich and desirable EM wave properties. We have characterized 3 different types of nanomaterials we have studied: the fractal electric nanomaterials, the fractal magnetic nanomaterials, and also recently the fractal plasmonics nanomaterials. And also we found that these nanomaterials, they share the common characteristics of the fractal structure. They have very good wavelength properties. They also have multi-band properties, and also they both can be characterized to behave like a very good nanomaterials. And many applications have been demonstrated. So this is the related applications. I think I just stop. Maybe you have questions for this part.
Why it can be realized? Is it because the permittivity or the permittivity is negative?
Oh, that's a good question. Okay, let me go back to the structure. So, why can we realize both T and TM? Let us go back to the structure. Because our structure is wavelength along all directions. So this structure is actually can be viewed as a local resonators. So when it is on resonance, the coupling between these two will give us a so-called a TM polarized surface plasma. The coupling from this resonator to this resonator will perform a running wave along this direction. And this direction, this mode will give us a TM polarized surface plasmas. So why the slit structure cannot? Because you can find that the slit structure is wavelength only along this direction. So it cannot form the running wave along this direction. No, it cannot form. Because for this direction, it is not in the wavelength regime. So the diffraction have destroyed everything all. So it can only support the coupling between the two resonators along this direction. And along this direction, you will find it only perform TM polarized surface plasma. So that's the key point of this structure. All dimensions are wavelengths.
Also in that structure, you use fractal structure. The purpose of using this fractal structure is just because the plasmonic structure can be multi-band.
Multi-band is only one advantage. I think the most important thing is that fractal structure can be very slow wavelengths. For the lower resonance mode, it can be very slow wavelengths. I have shown you that in the previous work, this very small structure can support a very long wavelengths. That is a very unique properties of the fractal structure. If you use a single structure, it can only support a half lambda resonance. So that's why we use the fractal structure. The slow wavelength structure is the most important consideration.
I had two questions. One regarding the PEM coupling. So we see the dispersion diagrams for PE and PM are not identical. So
yep.
The high K energy are different for PE.
No, high K is the same. But the slope is not the same.
No. Yes. Okay. So near gamma, it's almost identical.
This is not. This slope is different. However, this high K is the same. This frequency
yes,
and this frequency are
the derivatives are same. So is it because of different coupling factor?
Exactly.
Due to shape and isotope?
Yeah, exactly. The coupling between this one will form the slope of this TM polarized, this slope. The coupling between these two will give us the slope of this. However, for the high K, each one will be localized. So that's the identical frequency.
And the second question was, how is the SPP resonance frequency reduced? Is it just the fill factor?
Filling factor?
The filling factor of metal, or?
No, it's a little bit. Actually, it is some kind of. You can view this structure. This is actually an anti-structure node. So you can use the Babin's principle to transform this resonance to another positive structure. For the positive structure, you have a resonance, and the resonance given by the wavelength is roughly given by the current length along this complete structure. So you can view this for this slot structure.
Yes, please.
I have two questions. The first one is it possible to make the region of the different polarization cover the same region, cover the same frequency region? For now, you see that they are different, they are in different regions. The TEM polarization are in different frequency regions.
You mean for this one? For what one? For this one?
For this figure, you see that the T and TM polarization resonance
Yeah.
are in different regions, and in different frequencies.
No, for this frequency, this is the same frequency. This frequency and this frequency are the same.
I mean,
This is the same. This is the same. The only difference is that the only difference is the position. I mean the E field position. This is because our structure is anisotropic. This is the only difference. However, for this,
is it possible to make the same direction the TPM cover the same?
it is possible, but you cannot use the fractal structure because fractal structure is inherently anisotropic. You can use, for example, you can design a kind of symmetric structure.
In the previous PowerPoint, and you see there are different band gaps for the HC material.
Yeah.
But in these figures, there are different. You don't show the different.
Oh, it's still actually different. Actually, for this one, you can see that this is for E parallel to y-axis. So this is for E parallel to axis. So for the fixed E field excitation, these two resonance frequencies are different. That means still we have a different resonance for two different excitations.
How many resonance frequencies for this shift?
in principle, how many levels you have, how many resonances you have. But you have to be careful because for the higher frequency, maybe they do not satisfy the surveillance requirement, so we do not have surface pattern at all. But in principle, how many levels you have, how many resonances you have.
Another question is, have you done the experiment of the photonic material? Have you done it?
For this one?
No, not for this one. I mean, that is the structure and yield point 0.04 micrometers. That is structure. That is the structure.
Diode?
Yeah, in photonic frequency, you have shown us. Maybe the simulation is done.
Yeah, we are in collaboration. We are in collaboration with Danish group. We are trying to perform this correlation. Still not.
Still not.
Yeah, we are only perform the microwave experiment. Still not.
Which method are you proposed to which fabrication method are you proposed?
I think photolithography also EV.
Photolithography is impossible since it is 0.04 micrometers.
You know, EV maybe FID. For that design, maybe FID you should have. Yeah, we are in collaboration with the Danish group. They said they can fabricate this system.
Another question is, can you tell us the physical mechanism of the image split? Image split when you put the source use a boundary between two units.
Okay, you mean the images split?
Yeah.
Okay.
Why the image split?
Yeah. That's very easy to understand. Okay. Oh, sorry. Because at the boundary, you have equally distributed excitation field. I think you're talking about this one.
Yeah, image split.
Yeah, I think you're talking about this one. Okay. So at the boundary, you have both this resonator and this resonator. And your source can have equally radiated field for this excitation and for this excitation. So you can excite two resonators at the same time. So that's why here, on the other side, it split into the two images. And if you shift from the boundary slightly, you find significantly this image is much brighter than another one. Yeah.
Okay, are there more questions? If not, let us thank our speaker again.